Okay, so here is a example in the work energy, class 8. We're going to redo an example from class 7, and I already have a video for that one. It was called the difficult path example. This is the same example right here, but we're going to use work and energy, and we're going to find out that it's way easier to solve this problem using work and energy than it was to try to find. So what we wanted to do was find out what the maximum angle was going to be for this. So what we do is we start out, it's a good idea to create a datum. Right? And well, actually, one of the very first things I like to do is to write this out. K1 plus PE1 plus W1 to 2, or maybe I want to write U. You got to get back in the habit, right? Capital U equal KE2 plus PE2. It's something I did mention in the previous video. The book likes to use capital T for this, and they use capital V for PE, and I don't really like doing that. So I'm just using these two-letter designations. I think it makes a lot more sense to me. So what we're given as part of this is that the velocity at this bottom location is 4 meters per second. So what we could do is we say, let's write it out. I like to write this out right here and then write a list of this. So we have 1/2 mv, they're calling it VO right here, but I'm going to call this state 1. And I'm going to call something up here state 2 at another time right here. So this is going to be state 1 squared. So we could actually get the value for this right here and get what the velocity is 4. And notice right here, by the way, I think it's a good time to point out that the units that we're going to have a kilogram meters squared per second squared, right? That we're going to, so what part of that, the kilogram meter per second squared is going to be a Newton, right? And we're left with a meter. So this will turn out to be units of Newton meters, right? That's our energy units. And what we end up finding as part of this, I'm going to leave it a B right now. We could find out the value of the thing, but I didn't do it in my example, and I should have maybe. We got 30 times 16 right here. So we had 240 Newton meters. But I might keep it as my variables as I go down below, just to be aware. And now the PE1, what we're going to do is we're going to establish where the datum is. And let's just pick this as the datum. So that like right here is going to be the location of Y2 right there. That's where Y2 is later. So we by default going to set this as 0. And we're going through this equation one at a time. This is good practice. We take a look at this, and we're going to assume that there's no wind resistance, that there's no friction right up here. There's nothing going on right here. So this ends up being the conservation of energy because there's no external work taking place. We don't have a force pushing onto the thing, so we're golden. The KE2 right here, that's at state 2. Well, we're going to find the maximum angle. That by definition is going to be 0 because it's going to pause right there at the maximum angle. And then PE2 right here, what we're going to have is mass times the gravity times the Y2 right there. And we can write out Y2 over here, right over to the side, is right if this is the length right into there, right? This is going to be, right, this height right here is going to be the length times the cosine of that angle. I think someone's either giving me a call. That's the CVS from Old Saybrook is calling me for some reason. So they can go away. So we have the length of this. So we want to find this distance, and it's going to be this length minus this length. So it's that minus the cosine of theta right here. So we can just say mg L minus L cosine of theta. Now we could plug all of these things in here. I'm not going to plug this in here because we're going to see something interesting by doing that. But let's plug them in there. So we're going to say 1/2 mv1 squared. I'll put the zeros just to remind ourselves that they're placeholders. And we'll have a 0 right there. And then we're going to have plus mg L minus L cosine of theta. Something that's interesting is the mass cancels out right there. So the mass didn't actually matter, right? That's not necessarily intuitive. You would think larger mass, but that's the maximum angle given this of velocity right there is going to be set by this. So we end up with 1/2 times v squared. So that's 4 squared. It's going to be equal to, and we're dealing with the metric system, so we 9.81 and times the length. And let's bring the length out of this. And the length is 4 meters. So that's interesting. And I have 1 minus the cosine of theta right here. So what we're going to end up with is, if we do all these values right here, we'll say the cosine of theta is going to be 0.7961. So theta, which is going to be the maximum angle that's going to take place, that this thing can reach up to there, is going to be 37.24 degrees. And that matches with what we said in the previous example, in the example where we did the integration of the velocity to try to get it right here. So it's a much simpler type of approach, much easier.